Multi-Sector Dynamics Community of Practice webinar. This is part of our 2026 webinar series. Just so you know, we are going to be recording today's webinar. And so today's topic, modeling the operations of reservoir systems with LLMs and inverse reinforcement learning. Just as a little bit of background, in general, go ahead. We ask that you be considerate, respectful, and collaborative. Keep muted unless the facilitator calls on you to speak, and maintain a supportive and positive environment. Respect any questions or input from other participants. We're going to have the speakers, and then we'll have Q&A as part of the overall webinar. In the hosting group for this is the Multi-Sector Dynamics Community of Practice. So this is something that started in 2020, and it's been an effort to accelerate development of needed foundational capabilities of human Earth system science through open science and a growing transdisciplinary workforce. We've had a pretty strong presence in the global environmental change section for AGU, and we will again this year, so you can stay tuned. We'll have more advertisements for our AGU sessions, which there are several. Today, I will allow Stefano to introduce, but again, this is modeling operations of reservoir systems with LLMs and inverse reinforcement learning. Just a little forward advertisement. We have another webinar on July 9th, 1 to 2:30 EDT, and that's going to be focused on quantum computing futures through a multi-sector lens, which should be interesting, and I hope you join us for that as well. And then just in terms of finding us, so you can go to our portal, multisectordynamics.org, or find us in our LinkedIn group here. So both QR codes. And so with that, I'll pass to you, Stefano.
Thank you, Pat. Good morning, good afternoon, depending where you are. I'm Stefano Galelli, and I have the pleasure today to introduce our speakers and moderate this webinar with Pat and David Gold from the University of Utrecht. Pat, would you mind sharing the screen since you're already there with that?
Just give me 1 second.
Sorry.
No worries. All right, let's go ahead. Here you go.
Thank you. So as Pat mentioned, we have 3 speakers today. Matteo Giuliani will kick us off. Matteo from Politecnico di Milano, I should have mentioned, will start this series of presentations by showing us how inverse reinforcement learning can be used to infer preferences and weights given by reservoir operators. Second presentation would be by Rohan Wilkho from Cornell University. We will be transitioning from weights and objectives to inferring the reward function, so importance and rewards that we get that are associated to different combinations of state and actions, with applications to a number of dams in the US. And finally, Wyatt Arnold from Politecnico di Milano. We will be transitioning from 2 presentations on inverse reinforcement learning to large language models. So we will be moving towards a totally unsupervised, if you will, approach, and we will see how large language models and the use of specific prompts can be used to model different types of actions that have been taken by operators. Finally, before leaving it to Matteo, let me remind you that we will have a Q&A section, but we will have that at the end of today's webinar. If in the meanwhile you have any question, just please write them in the chat so we can keep track of the questions being asked. All right. Thank you very much. Matteo, I leave it to you now.
Okay, thank you, Stefano. And again, good morning, good afternoon, depending where you are from. Italy, and my pleasure to be here and kick off this webinar with first application of inverse reinforcement learning and a sort of overview that I hope will also be transversal with respect to the following presentation that will follow my contribution. So okay, so just to frame a little bit the problem being my presentation, the first, I think is good to provide a little bit of the context with respect to the overall event that we organized today. And so, first of all, is something that we all know is somehow one of the core concepts being studied by multi-sector dynamics is this idea that natural system or pristine river basin are becoming less and less common on our world, and that the human footprint is becoming more and more evident. And so this poses challenges and generates motivation for advancing the representation of both natural processes as well as the human control and the human influence on such processes. And so going into the direction of a couple systems where humans are playing a bigger and bigger role. And this is particularly relevant for a modeling community where over the past few years, most of the emphasis was on the development of system models for climate applications that are becoming extremely powerful, extremely sophisticated. We can now run simulations at kilometer scale resolution that were basically impossible up to a few years ago. At the same time, this development has been primarily focused again on the representation of the natural component of these systems. And so the question here is how we are able, how much we can go into the direction of embedding also the human component in such modeling tools. And so here, just want to provide a little bit of the context because before entering into the detail of the application that we developed, trying to frame the different school of thoughts related to how we can model human decision and human behavior in general. And so if we look into the literature, one pretty common approach is to go into the direction of developing descriptive model. Now I'm using descriptive models. I also know that there is a variety of terminology to refer to this type of approach. So just let me stick to that for the sake of clarity. But the main idea here is that we can collect data, we can observe behavior of human people that are taking some action in some conditions, and ultimately we can try to understand what is the typical action that is made in a given condition of the environment. So this can be implemented in a variety of ways, from very qualitative approaches, somehow derived, inspired by the social sciences, to more quantitative approaches, maybe in the engineering domain, when ultimately we are building a sort of regression model at the end of the day, with more and more capabilities that were opened by machine learning and deep learning algorithm, but at the end of the day is a sort of regression line that tries to reproduce observed action with respect to observed states of the environment. Can we do this for reservoir system? Obviously, yes. So the idea, if we move this generic description into a reservoir system, is that we may want to reproduce, for example, the controlled release from a dam. And this can be a function of a variety of variables that we can observe in the system, such as the water availability in the reservoir upstream of the dam, the inflow dynamics. If we're talking, for example, about hydropower reservoirs, maybe the energy price or the energy demand can play an additional role. But again, at the end, it's just a matter of running a sort of regression where we build a function that, given this condition, determines the release. And if we have availability of observational data, this is something like a supervised learning task that we can solve with traditional statistical regression or machine learning approaches. We did an experiment back in time with Andrea Castelletti and some colleagues in Milan trying to reproduce the operation of an alpine hydropower reservoir, and results, not surprisingly, are quite good. Again, if data are available, we do have the tools for making this modeling task. The second school of thoughts instead approached the problem with normative models. primarily inspired by economics, so somehow suggesting that under the assumption of full rationality, humans are behaving in order to maximize a given utility function, and so the actions that are made are the ones that are thought to maximize this utility function under some assumption about knowledge of the system, observability, and so on. So can this be done for a reservoir operation? Again, yes, it's a matter of formulating optimization problem or technically an optimal control problem. And again, in the case of hydropower reservoir, this is basically deriving an operating policy that is maximizing, for example, the revenue for the hydropower company. Is this something that works? Again, there is plenty of examples here. I'm reporting a collaboration we did with Pat, again, more than 10 years ago, where we were maximizing the profit for an hydropower company, and this behavior was quite close to the observed dynamics in the system, somehow deriving operating policies that were also rational with respect to the price dynamics, suggesting to release more when the price of the electricity is high during weekdays, less overnight, even less during the weekends, and so on. However, those two approaches were developed primarily in parallel, and neither of the two is somehow perfect, because on the descriptive side, there are some limitations somehow associated with structural uncertainty with respect to the shape of the regression function that we're using, and low transferability to different contexts because it's strongly relying on observed data, and there is variability, and so risk of overfitting and so on. On the normative side, also, we have limitation, strong assumption related to the full rationality of the operators, and then the difficulty of handling multi-sectoral system and preferences that are not associated with a unique, very clearly defined utility function. And so here is where we developed our approach, so trying to somehow move from observed action to hidden preferences with a strong focus, as Stefano was mentioning before in the introduction, on multi-purpose reservoir system. So the underlying idea of our work was to see whether observing the dynamics of a regulated reservoir, we can infer the historical preferences associated with a specific trade-off among competing interests that we know are influencing the way that the reservoir is being operated. And so to tackle this problem, we developed an approach in the direction of implementing an inverse reinforcement learning framework. So I don't know how much you are familiar with that, so I'm trying to provide a high-level introduction to that. And so the overall idea is ultimately to start from a traditional reinforcement learning scheme where we have an agent that is interacting with an environment, is able to observe the conditions, so the state of the environment, given that condition is making an action according to a given policy. And then after the action is executed, there may be some stochasticity in the dynamics of the system, is then getting a reward that quantifies the benefit or the cost of making that action in a given condition of the environment. And so in traditional RL application, the idea is to focus the attention on the optimization of the policy such that we can maximize the reward for the agent after implementing the policy over a long simulation or in the real world when that is possible. Then if we move from traditional reinforcement learning to inverse RL, the idea is to move the attention, to move the focus from the policy to the reward definition. And so somehow to search for a reward function that is making the observed policy, the observed behavior, rational and fully optimal. And so here we made the application using a case study located in the north of Italy, which is Lake Como. This lake here in the middle of the map, which is south of the Alps, is getting a lot of water, primarily during the snowmelt season in springtime, and then is distributing this water to a large irrigated area in the Pianura Padana, so south of the lakes, with a mismatch between water availability driven by snowmelt in springtime and most of the summer irrigation demands required by the farmers. This system, however, is also operated for other two reasons. One is associated with flood control because storing too much water into the lake is generating risk of flood in the city of Como, located on the lowest point of the lake shoreline, here on the western branch of the lake. And at the same time, there are touristic and environmental concerns related to the fact that the water level of the lake is getting lower and lower. And so this creates a three-dimensional objective space that is influencing the way the operator is making decisions in regulating this lake. So we try to infer this historical trade-off between these three objectives, having availability thanks to a long-standing collaboration with the water authority, having availability of a long data sets of observational data at the daily resolution. So actually, we do have data that go back into the middle of the previous century. Here, the study was developed considering only the last 20 years, also to remove some non-stationarity with respect to the observational records. And so here you see on the left the time series of the water level of the lake, on the right the associated release. And so here what we did was to apply this specific IRL algorithm, sigma-GR, or a gradient-based IRL algorithm that was able to identify a specific compromise, so a specific weight vector that determines the preferences the operator used for balancing the competing interest of flood control, low level, and water supply. And here we can notice that a strong priority was given to flood control. This was also somehow confirmed during the interaction we had with the stakeholder for a variety of reasons that we can also discuss later on in case you're interested. Then a 20%, 16% preference for water supply, almost no preference for low level, which indeed is a concern that emerged relatively recently with respect to this 20-year time period we use for our analysis. Then the question is whether these inferred objectives is able to reproduce reality. So what we did afterwards was to take this trade-off solution and then solve a traditional forward RL problem, determining with a direct policy search algorithm the optimal controller for the dam for that specific trade-off point. So we solved the problem, we obtain a simulated trajectory now under this optimal policy. And what is nice to observe is that this simulated trajectory now is able to reproduce quite well the observed dynamics, both in terms of lake level and lake releases. So this somehow open our interest and stimulated further research direction into the development of these approaches, which have been shown to produce interesting results. Now, trying to wrap up the main takeaways messages from this presentation. There is also the QR code on the slides in case you want to read all the details in the paper that describes this application. I think this first application is showing how the human decision is relevant, and there is the need of improving our capability of representing human decision for evolving Earth system models in representing the coupled dynamics of the human and the natural systems. And in this context, inverse RL provides a quite attractive approach that is data-driven, so it's based on observed behaviors, but is also able to uncover hidden objective, hidden preference behind such observed decisions. And overall, this learning of the human objectives can enable the simulation of the coupled dynamics between human decision and evolving system dynamics, potentially also accounting for long-term trends, climate projection, socioeconomic development, and so on. So that's it from my side. Thank you for your attention. I will hand over to the next speakers and happy to take questions during the Q&A at the end of the webinar.
Yes. Thank you, Matteo. Thank you, Stefano and Pat, for introducing and getting started with the webinar. Okay, good morning, good afternoon, good evening, everyone, wherever you are. Carrying on from Matteo's presentation, in this particular research work, what we'll be looking at is looking at inverse reinforcement learning as a framework to decode decision-making in managed hydrologic systems. The motivation kind of stems perfectly from what Matteo described, like human decisions have rewritten the water cycle, so much so that 61% of Earth's surface water storage variability occurs in human-managed reservoirs. Researchers as early as 2014 have started considering the fact that human intervention can often exceed the impact of climate change on our water cycle. And third is that only 37% of world's longest rivers remain free-flowing as of 2019. Therefore, decoding the decisions behind this water variability is very important for us to effectively manage the water systems on which many of us depend. In this study, we focus on reservoirs because of the primary reason that reservoirs are multi-purpose, serve multiple purposes. And in order for them to serve those purposes, agencies which operate these reservoirs come up with something called the operational targets, which are prescribed levels of storage in water control manuals. As we can see in the two curves, where the reservoir on the left is expected to have a uniform storage throughout the year, and the reservoir on the right is expected to have a seasonally varying storage. But what makes reservoir operations even more complex is the fact that operators routinely deviate from these targets, as we can see from the blue lines, which is the median or the mean of the storage throughout the year in both the reservoirs, which in some cases we see exceed the targets set by these agencies. So therefore, this kind of makes the motivation behind reservoirs as our case study to decode the human operations. When it comes to the current frameworks for characterizing reservoir operations, they can be broadly classified into three categories: optimization-based methods, data-driven methods, and rule curves. However, each of them have their own limitations wherein, as Matteo mentioned, for optimization-based methods, we assume a rational behavior. Data-driven methods are exhibit more black box behavior, which challenge interpretability and generalizability. And rule curves often simplify complex decision-making processes. What these do not capture is the specific reward landscape of the state and action that the particular reservoir operator is trying to optimize for. So the question that we are trying to answer through this research is, one, can inverse reinforcement learning help us recover the latent objectives or the latent intent that governs reservoir operations? And then second, if it is possible for IRL to do so, which algorithm does so most robustly? Moving on to the framework, in this particular study, we we looked upon the reservoir operations as a Markov decision process, which are defined by state, action, a transition function, and a reward function. The reward function is essentially the function that we are trying to decode using inverse reinforcement learning. In this particular case study, the state variables that we considered were the storage, net inflow, and the month of the particular operation. The action is the release that the operator makes. This release then interacts with the environment through a mass balance equation. And we have these observational records. We use these observational records as an input for the inverse reinforcement learning algorithms to infer the hidden reward function. In this particular study, like in this presentation, I will be going over just the crux of the two algorithms that we are considering and how they, in fact, infer the reward function. For the sake of simplicity, I'll be talking about them at a very abstract level. The first algorithm that we consider is the adversarial IRL, which essentially learns to decode the human behavior through a competition between a policy generator and a discriminator. What we essentially have are two parameterized functions. We have a generator and a discriminator. The purpose of the generator is, given the state, it needs to predict the action that the reservoir operator is most likely to take. Depending upon the action, this then interacts with the environment. We have the next state, that is the next storage, and we have a sequence of what we call generated state action trajectories or generated storage release trajectories. The discriminator then compares these with the observed state action trajectories to predict or to be able to distinguish between the generated and the observed trajectories. The output is essentially a probability that the trajectory is from the expert. Now, if a discriminator is powerful enough to be able to distinguish between the generated and the observed state action trajectories, it means that our policy is not yet strong enough. So we move on to the next training cycle where we update the discriminator as well as the generator. However, when the generator is able to fool the discriminator, such that it is no longer able to differentiate between the generated and the observed trajectories, it is then that we have the reward function emerging from the discriminator and the policy emerging from the generator. This is one class of algorithms that we look in this particular study. The second class is the inverse soft Q-learning, which infers the implicit reward, albeit through a different methodology as compared to adversarial IRL. It learns by assigning high values or high reward to the expert actions at a given state compared to any other alternative action that the policy could take at that given point. This essentially is termed as advantage of the given state action combination. In this case, again, we have two parameterized functions. One is a Q value function, and the other is a policy function. The Q value function takes in the observed state, action, next state transitions, that is storage, release, and the next storage transitions. And it basically outputs a metric called the advantage at that given state action combination. The policy function, as very similar to adversarial IRL, works to predict the action given the current states. Now, in this case, the training happens such that the Q value is updated, or the Q value function is updated to maximize the advantage of these expert actions, the observed actions, as compared to the actions from the policy function that is being trained. Whereas the policy function is trained such that it is able to predict actions that have high Q values. And at convergence, that means when the Q values stabilize across iterations, the policy emerges, the control policy emerges from the policy function, and the reward emerges from the Q value function. In this study, we had considered 9 different reservoirs. As we can see on the map, they had different storage capacities and served different operating purposes. We had some dams which were severely multi-purpose reservoirs, and some which were hydroelectric, flood control, and so on. So the purpose of having such a varied combination of dams was to compare the two algorithms, adversarial IRL and IQ-learn, and to see which algorithm is able to decode the intent most uniformly across this diverse set of reservoirs. When it came to observational records, we used the ResOps US dataset, applied a bunch of pre-processing steps to come up with mass balanced checked reservoir operational records. After doing all the pre-processing, we found that we had 18 years of consistent data across all the 9 reservoirs. So we eventually chose 14 for training, 1 for validation, and 3 for testing. For evaluating the different IRL algorithms across the 9 reservoirs, we considered a bunch of evaluation metrics. One of them was predictive accuracy of the control policy simulation. We used the Pearson correlation and the normalized root mean square error. We also compared our IRL algorithms with 2 state-of-the-art bench baselines, the StarFit and a conditioned LSTM. We had also taken into account the reward function interpretability. That means how much do the reward functions align with the observed demonstrations and the operating purposes of the reservoirs. We had something called the Shapley values, which are model agnostic interpretation techniques for explainable AI. And in the end, we also compared the algorithms on the scale of computational efficiency. So moving on to the results. So when we compared, for the sake of simplicity, this particular slide has only 4 reservoirs, but I have the results of other reservoirs in the appendix. We can see from this particular table that apart from one reservoir where one of the metrics is the best performing, across all the other reservoirs, we see the IRL algorithms to be the one which overperform or exceed the performance of the baselines. The other thing that I'd like to point for all of us at this from this slide is that the performance of both the algorithms, adversarial IRL and inverse Q-learn, are more or less similar across the different reservoirs. And the point that I'm trying to make from this is, I'll come back to this and why, despite having similar performances when it comes to predictive accuracy, one of them still overperforms the other when it comes to reward function interpretability. For simulation, we essentially had results like for one of the reservoirs, we had that the storage and the reservoir release patterns were more or less matched by the IRL algorithm, but as we progressed ahead in time, we observed a certain lag in the predictions. For some of the reservoirs, we found a perfect near perfect release prediction. However, the storage predictions were way off. For the other reservoirs, we found near perfect storage as well as release predictions throughout the 3-year testing period. Moving on to reward interpretability. Now, when it came to interpreting the rewards, we had essentially considered how well do the reward functions align with the expert demonstrations. One point of note that these IRL algorithms assume that the expert observations are optimal. And when we look at this reward function, where a darker green region means high reward and a lighter or a darker red region means lower reward, we would ideally expect that these magenta dots, which are the observed values, to align with the higher reward regions. In this case, the absolute value of the reward function hold little to no importance. It is only the relative distribution of the reward function, of the reward values, that is of concern or is of importance. This is the reward function recovered by adversarial IRL, where we see that the observed values do not align with high reward regions. However, when we move to the reward regions of inverse Q-learn, we see that in that case, the expert observations more or less align with the high reward regions. And this particular reward function also reveals that in the state of New Mexico, when during the flood season, preempting the flood season, the operator starts making more release starting from March until November, where the flood season is essentially between June and September. So therefore, it is essentially fulfilling, we can see that the reward function that we recover from IQ-learn essentially shows that how the operator is fulfilling the flood control purpose in New Mexico. The other reward function that I would like to discuss today is regarding Engelbreit. Now, one thing to note here is the Engelbreit is supposed to maintain a uniform storage level as per the US Army Corps of Engineers, but we see that from the previous years of pattern that the storage is anything but uniform. This is important for us to be able to interpret which reward function is accurate. Adversarial IRL recovers a reward function where we see a particular horizontal band of storage, which is most of high reward. And if we just go by the definition of a uniform reservoir where a constant level of storage needs to be maintained, we would assume that the reward function recovered by adversarial IRL is correct, where only a top storage band is of high reward. However, as we see in the past, in the observational records, the storage is not uniform across the years. Therefore, it gives us the impression that the reward function recovered by inverse Q-learn is more interpretable for this particular reservoir, where the behavior is very contrary to what one would expect. In this case, what we see that the reward functions are nearly storage independent. This indicates us that the reservoir operator at Engelbreit may be operating on an inflow-driven basis, or maybe more like a runoff river, as a runoff river reservoir. This is also confirmed by the contribution of these variables or the state variables towards release decisions across the year. What we see on the bottom left is the contribution of storage and inflow towards release decisions on each month as inferred by both adversarial IRL and IQ-learn. And we can see inflow by far dominates storage for this particular reservoir. This gives us the impression that although the classification of Engelbreit is uniform, it is essentially, the operator is essentially functioning as an inflow-driven reservoir, which also, if we link it back to the predictive accuracy results, that while adversarial IRL and inverse Q-learn, both of them gave similar performance metrics, it is only after inferring the reward functions that we can ascertain that which IRL algorithms are more suitable for this purpose, and that predictive accuracy may mask the underlying behavior. Yeah, for the sake of time, I would just skip through this particular slide. This particular slide essentially states the same thing, that both Conchas and Engelbreit are classified as uniform reservoirs, but the contribution of storage is higher in Conchas towards release decisions, as one would expect, whereas the contribution of inflow is much higher in case of Engelbreit, which leads to the possible conclusion that it is being operated as a run-of-river reservoir. Take-home messages from this presentation that we see that IRL helps us recover physically coherent reward functions with higher predictive fidelity as compared to baselines. We also see that data-driven methods that optimize for predictive accuracy alone may just clone behavior. They may not recover the true underlying control policies and intent. We also see that the reward function is not just a performance metric. It can be seen as an institutionally diagnostic tool. A few acknowledgements regarding funding and computing resources. And with that, I pass on the presentation to Wyatt. So thank you all. And I look forward to taking your questions.
All right, I will jump in now. Okay, so yeah, I'm Wyatt. I'm really happy to share this work today that I did with John Herman at UC Davis, and Matteo Giuliani and Andrea Castelletti at Politecnico di Milano. A large language model as a reservoir operator, bridging human judgment and optimization in water resource systems. So in multi-sector dynamics, we carefully build models of water, energy, and land, but these systems are run by people. And human judgment is difficult to represent in these models, as we've seen and all know. In the water sector, system managers balance supply, flood control, and the environment, weighing all these goals that are very difficult to formalize as an equation. So in modeling, we basically approach this in two ways. We can replicate learning from historical data, fitting to what operators did. This gives us behavior, but crucially, no decision logic. So it's challenging to generalize, and it's limited in its explanatory power. On the other hand, we optimize. This is powerful, but of course it needs that objective function. And for real multi-purpose systems, nobody can really fully specify what that is. It's also the fact today that after many, many decades of research and tool building, there are operators of large, very complex water systems that still prefer Excel spreadsheets and simplified tools. So that does indicate something, too, about the practical utility of these methods. So we are experimenting with this idea that language models can perhaps bridge these two paradigms. Recent work shows that they resemble human behavior and economic and cognitive tasks. This is the examples on the left here of recent research. And then on the other side here on the right, we can see that their reasoning improves. It gets better and better with more test time compute. So the question is whether a model that interfaces with language and can reason through a problem, whether this type of language model can act as a bridge to both interrogating how we manage these systems and how we might manage them better. So to answer that, we created a test where we can directly check this idea. Reservoir operation is an ideal case for these three reasons that I listed here. First, It is a hedging decision under uncertainty. Every month, the operator decides how much to release, trading a shortfall today against the risk of a worse shortage later. Hedging is well studied in reservoir operations, so there's a very deep literature to benchmark against. Second, we have a ground truth. These systems have been run for decades. We can compare any model against what real operators actually did. And third, we have a formal optima. A simulator plus dynamic programming gives us best case reference and a dial for risk aversion, so we can place a model on a spectrum from naive to human to optimal. So we test this on Folsom Lake, and a reservoir on the American River in California. It's a very challenging reservoir to operate. The winter inflows are very large, very variable. The demand peaks in the dry summer, with supply dependent on the spring runoff. And crucially, some storage is necessary to carry through these multi-year droughts that the environment faces. If a language model can operate Folsom sensibly, that might mean something. So here's how we set up the comparison. The language model is a generative transformer. We're using OpenAI's O4 Mini, was released last April. At this point, it's probably been, it's reaching almost its deprecation point. Anyhow, this is the model that we experimented with as part of the main experiment. It's trained to produce human-like text, and it's post-trained to reason step by step. And it has not been trained on this problem that we're testing it on. So we consider it an unsupervised application. Now recall the two sides of that bridge, replicate and optimize. So for the replication part, we were benchmarking a neural network regressor, a multi-layer perceptron, trained directly to reproduce the historical operating decisions on a monthly time step. And for optimality, we have dynamic programming. The deterministic version obviously assumes perfect foresight, gives an unattainable lower bound on the shortage performance, and the stochastic version gives a more realistic closed-loop optimal policy under uncertainty. And for both of these, we obviously have the knob of risk aversion, that the penalty exponent, the beta. And so our question is where the language model lands between these two, replication optimization. And this is interesting, given that the language model wasn't trained to operate a reservoir in a supervised way under a specific objective. But it certainly, we understand it was trained on lots of scientific literature, almost certainly including the papers of some folks here, as well as information that's been published online about water resources system management. Okay, so how do we ask the language model to operate the reservoir? Every month, it gets a prompt in 3 parts that mirror what the Folsom operator has. The system context sets the scene. It says the goal is to minimize shortages, describes the reservoir and its climate, gives the operating limits and the average conditions, notes that a seasonal forecast is available, and explains how an allocation percent turns into a shortage volume. But we never write down the penalty function. We never tell the model exactly how to hedge. We do give some general guidance. In your determination, consider the volume currently in storage, inflow to date compared to expected inflows, and the need to balance meeting current demands against conserving water for future demands. And we also slip in an irrelevant concept not shown here, kind of like a red herring, to test whether the model says that it matters, that irrelevant concept. The observation, every step, it receives an observation of the current state, current storage, inflow so far during the water year, remaining demand for the remaining part of the water year, as well as the mean 10th and 90th percentile forecast for the remaining inflow for the water year. And that's drawn from the hindcast available in the system, as well as last month's allocation. So the previous allocation decision that was made, which was also an output of the LLM. And the required output is a structured JSON, and it's first and foremost an allocation from 0 to 100%, followed by a request for a short justification for that allocation, and a ranking of how important each input concept was in the system context and observation prompt. And so 2 choices matter here. Each month is an independent call. There's no memory. In other words, we don't chain previous decisions into the prompt. So the model behaves kind of like a policy, mapping conditions to an action. And we never give it a hedging rule again. So any risk-averse behavior really has to emerge from the LLM's latent, its own training. We're not trying to steer the LLM to hedge in a certain way. And one run is 252 monthly decisions over 21 years. Okay, so here's one way of viewing the results. This is the cumulative distribution function of daily water supply shortages over 21 years, starting with the baseline release demand policy, which just releases whatever is asked whenever it physically has the water. It will meet that demand. It meets demand 91% of the time, but it produces rare catastrophic shortages up to 9.3 thousand acre feet per day, which is essentially a full failure to deliver. It's a 100% shortage. But for the total shortage volume, this is actually the optimal policy. And so we use that as kind of, we'll compare the historical MLP and LLM against this 0 point. So as we can see, real operators do something very different. They hedge. As we all know and have understood, and it's been well studied. They accept frequent small shortages so they can avoid the severe ones. And historical operations therefore meet demand only about half the time, but they cap the worst case near 5.2 thousand acre feet per day, which is less than half the standard operating policy extreme. The MLP, as we expect, closely replicates the historical pattern. In this case, the poor fit actually results in better overall performance under all three penalty conceptions, linear, quadratic, and cubic. And now for the language model, it sits between the standard operating policy baseline and the historical operation. It meets demand 55 to 65% of the time. Each one of those little slightly transparent lines is an independent run over that 21 years. So we can see kind of the stochasticity and the decisions and the state carry affecting those decisions. But it does expose the system to worser shortages in the deeper droughts, up to 7.8 thousand acre feet per day. And so as we can see, when shortages are penalized, that large deficits hurt more than small ones. The language model tends to beat the standard operating policy. Okay, and then the final benchmark, of course, is the SDP and the DDP. So when we look at this comparison to the traditional approaches for optimal reservoir control, we actually don't know what the true utility function is. And so we actually optimize the DDP and SDP against a range of beta exponents. That's the SDP shows the range most clearly there. DDP is less sensitive because it can find that optimal policy for across all betas. But here we basically see that the LLM is doing the best on the cubic shortage, but it's not quite as risk averse as the MLP or the historical. So it sees reduced frequency of smaller shortages. But the key here is that, like SDP, you need to raise the beta quite high to even sort of reach where the MLP or the historical was in terms of cubic shortages. So this is, we think, kind of impressive, given that no LLM fine-tuning was done. And so the LLM seems to have some inbuilt notions of reservoir operation and a precautionary pattern toward future shortages. Okay, so here, alongside each location, we do get that short justification. The final summary is here. It's reporting that this final summary is not the chain of thought that actually you can interrogate and extract from the model output. That it tends to be much longer. But here in the summary, you can see in this dry year of 2008, which is about half the normal inflow, in March, every run is still allocating about 100%. Working through the storage and forecast numbers, it leans on the pessimistic 10th percentile case. And then by June, as conditions worsen, every run cuts back, and the justification starts to reason about holding a storage buffer for the next year and for environmental flows. So the model is giving some clear, recognizable water management reasons for making those allocation decisions. But a summary like this is only what the model reports. A lot of recent work shows that LLMs, what they report is actually different or not fully representative of what's actually driving the sort of internal forward pass of the inference. And so we did an ablation test, a prompt ablation test to see if we could interpret the faithfulness and really get an understanding of what is actually driving the LLM decisions. So I'll show a sample of that here. So again, to orient you, how the result is shown here, this is with all the simulations shown so far. Squared shortages are along the bottom, cube shortages are up the y-axis, and the color ramp is the total shortages. So the best policies from a risk-averse perspective sit at the lower left near the DDP solution, and the standard operating policy is sitting up there closer to the top, and then the full LLM prompt, sort of the result I had shown on the previous slides, is there near SDP, doing somewhat better than historical. So from here, we change one thing at a time and watch the LLM performance result move. So starting with disabling thinking. So we turn off the chain of thought and the point jumps up. So this is clearly worse on the severe shortages that matter most. So again, that test time compute phenomena where the reasoning that the model can do, spending time sort of processing and spending time on inference and emitting tokens before it commits to a final allocation number that's doing real work. And so this reasoning phenomena, right, it's now the standard in the frontier models. Now, moving on, let's strip the prompt down to a bare instruction that just asks for a number from 0 to 100, and it basically collapses to a naive corner. That's the worst performing allocation output for this system. So we can see that basically the context is definitely holding it all together. We can add the context back in pieces, so we can tell the LLM that it's running a water supply reservoir. And just that information has it climb at least part of the way back. And then we give it the monthly observation state, but none of the written framing, none of the system context. And actually, it almost returns to the full prompt performance. And so in the paper, we go further and we ablate each part of the prompt on its own: storage, inflow, demand, the forecast. But I don't have time to walk through that all here. And then when we get back to the full prompt, and now we modify the goal. And so this gets it a little bit about now steering the model. And so we rewrite that single line of the goal to minimize large shortages. So we add the word large, and we say to protect end of year carryover. And the model slides down towards the optimal corner. And so we can steer its risk posture in plain language. So what do we take away? First, we find that the LLM is producing sensible, risk-aware decisions from context and observation alone. We interpret the language model simulation as a bridge between human judgment and formal optimization, with no hand-specified objective or operational rule, no task-specific training in this application, and it produces a result similar to human operators, but also approaching the performance of an optimal closed-loop policy. For our community, we think that it points to kind of an interesting new way to simulate the human side of water systems. It's kind of a virtual operator we could interrogate in plain language. We can steer it. And this is a first step in that direction, a baby step. And there are real limitations, as we all know, and becomes more controversial as the days go by. We can't be sure that its stated reasons match what it actually computes. There's a real risk of automation bias. So if we start to think about, in an operational context, this becomes very, very unclear. And so, for example, automation bias, these fluent explanations could make operators trust a model more than its accuracy warrants. And the outputs are very sensitive to wording. They're inherently stochastic. So again, a major issue for potential operational use. And then there's many directions to go from here: reliability and bias, incorporation of multiple objectives, kind of getting back to all the formal, really exciting work that Rohan and Matteo were presenting. So multiple objectives, multiple agents, multi-sectoral applications. We imagine a lot of interesting questions around non-stationary futures as well. After all, replication and optimality approaches struggle a lot with stationarity. And so this case of using LLMs might represent an interesting edge that this type of massively scaled, unsupervised learning approach could have. And then there's huge scope for enhancing and advancing interpretability, along with extensions around tool use and stateful architectures. That's my presentation. Thank you.
All right, thanks to all of the speakers. I'm going to jump in just with some questions since we're short on time. So Bing Lee in the chat wrote a question for Wyatt, which was given some of the vulnerabilities that you mentioned. Do you believe that in practical flood dispatch engineering, we should completely abandon letting LLMs directly output operational values and instead pivot towards a hybrid architecture where LLM functions strictly as a top-level reasoning agent and then dynamically invoke traditional optimization tools like SDP to enforce hard constraints? And have you and your team explored this type of agentic orchestration in any of your recent work?
I think that idea should be tested. I think that's one of the directions to go in, to basically provide the LLM the computational tools that we already have developed, and see how the LLM uses those tools to make different decisions. So my work was really much just a baby step. I think that this is exactly the kind of questions that we should be thinking about. Some people should research. Yeah.
Excellent. Thanks, Wyatt. I guess I'll just go ahead and read the next question from Nisa. For Wyatt, why do you use DP and monthly time step rather than LP and weekly time step? And has your DP solution been deployed or developed using perfect foreknowledge of all monthly inflows?
Sorry if I wasn't clear. Actually, the SDP and the DDP were optimized at a daily step. The MLP was optimized to make a monthly allocation decision, basically the monthly average release or the monthly average allocation, which was set at the beginning of the month. And that's exactly how we ran the LLM. So we don't prompt the LLM every day. We prompt it at the beginning of the month to make a single allocation decision that's spread across the future time steps. But all the simulation happens at a daily step.
Excellent. I'll just keep going with these questions then. Jenny Rice is interested in understanding your thoughts about incorporating perfect information about the forecast and/or the operational preferences and risk aversion. The forecast can never be known, but the latter are knowable for the model evaluation.
This actually just triggers a recall of an interesting paper, forgetting the author name. But basically, they tested forecast information against, they surveyed forecast information for making decisions with a panel of some researchers as well as reservoir operators, and to try to infer the value of the forecast and the value of getting a perfect forecast. And so I think a similar work could definitely be done here. But it raises all these other challenges that I think I kind of alluded to with using LLMs, right? So I think you'd have to be able to do both together to really to not derive any to not like say, oh, what the LLM is telling us is exactly how people would treat that value.
Excellent. I should say that we're at time. I think we could stick around for a minute or two more if folks have other questions. But otherwise, I want to make sure to thank everybody for coming and thank our excellent speakers for those wonderful presentations.
Yeah, likewise. Dave, sorry to interrupt. I think we can go just a few minutes longer. There are a few more questions coming up. So, if Matteo, Wyatt, and Rohan don't mind staying here. I'll read the next question. That's from Sarah Fletcher. Okay, so for the IRL folks, so this would be for Matteo and Rohan. Are there multiple possible reward functions that could lead to the same optimal policies? And if so, how do you handle that?
So, from my side, Sarah, the challenge is that we are actually facing in these days is slightly different. It's more related to the fact that there are multiple trajectories that result in similar objective or rewards. And so that is creating a bit of noise in the overall pipeline because it's somehow I mean, you could have very different dynamics in terms of release and level that are potentially resulting in similar objective values. Say, for example, if there is the flood threshold, you can get to exactly the same flood events, but then when you are in no flood condition, the level can be very different. And this is creating quite a substantial complexity into the detection of the objective and the reward function associated with trajectories that are very different. The one you say so is multiple rewards that lead to this policy. I suspect it might be a similar one. So it could exist. We didn't encounter yet in our research. I don't know, Rohan, if you happen to have examples in that direction.
Yeah, means I understand the question. So the inverse problem is an ill-posed problem where we can have multiple solutions for the same control policy. So I understand that. One way which I have thought about like countering for considering that is like we can have an ensemble of models. Like we can have different models trained on the same time period, and then we can have an ensemble to have so that we are making the decision based on multiple models and not just one model. Or we can have for the same reservoir, if it's stationary operating conditions, then we can train it on multiple time frames and then take the ensemble. So ensemble models can help us overcome this issue. But yes, solving inverse problems is ill-posed, yes.
All right, one final question before closing. This is again for Matteo and for Rohan. While learning from the operators without first evaluating how good their decisions were with respect to the objectives for which dams were built for.
On our side, the point is that there was not clear definition about the objectives that motivated the dam construction, and so even when the information is available in some data sets, also the data that Rohan used now, just tapping, then Rohan, feel free to correct me if I'm wrong, is somehow expressed as water supply or flood, but then is quite vague in terms of the mathematical formulation you can derive for that type of objective function. So if we say about flood is that the water level excess, are we talking about frequency of events or there may be a variety of ways also representing the same qualitative objective definition. So this goes, the qualitative version is the one Wyatt was exploring with the LLM, but then in the IRL part, we need to specify formally and mathematically the objective function. And that formal mathematical formulation is rarely available in my experience. And then often when we do have the multi-purpose system, even assuming we do have the mathematical formulation of the multiple purposes, the question is how are they balanced? And that is the second complexity that is often in information that is not available.
Yeah, and thanks, Matteo. And if I may, like the whole motivation of the fact that we are using IRL to infer objectives is the fact that we don't know like what are the specific objectives and how they are optimizing for or how they're fulfilling those objectives. So even for the question like how good were the decisions with respect to the objectives for which the dams were built, for that also I think understanding or maybe like decoding the underlying intent is a precursor, and we can use that to see like if they are fulfilling the purposes in the way they were built. But I think for the question uncovering the underlying intent becomes a precursor to diagnose the operations.
Right. Well, Sarah has an excellent question in the chat, but unfortunately, I think since we're already over time, we have to close. So I want to take one more moment to thank our speakers again and thank you all for coming. and remind you to keep an eye out for the webinars that we'll be organizing in the future and the next MMC webinar that Pat mentioned in the beginning. So yeah, have an excellent morning, afternoon, or evening, depending on where you are, and we'll see you at the next one of these.
Thank you.
Thank you, everyone.